In this video, we will talk about a shortcut for evaluating infinite limits of what we call rational-like functions. So we have rational functions like in part A, which are polynomials divided by other polynomials. But I introduced the term rational-like to include things like in part C, the numerator here isn't exactly a polynomial because of the square root term, and that's a fractional power. But the same technique is going to work. All right, so our strategy for these is we are going to ignore all the terms except the highest power terms in the numerator and in the denominator. So in the numerator and the denominator. And the motivation for that is, we've seen before that the highest power term dominates the growth as x goes to infinity or as x goes to negative infinity. It's growing way more quickly than the lower power terms. So in part A, we have this limit, and we actually saw this in the previous example in the last video, but we did it without this shortcut. So the shortcut's going to say, okay, the highest power of x on the top is this, negative 4x squared. On the bottom, it's the 2x. Let's just keep those terms. So we get the limit as x goes to negative infinity of 4x squared over 2x. Now we could simplify that, negative 4x squared. Simplify and get limit as x goes to negative infinity. And that simplifies to negative 2x. Now I can plug in to get negative 2 times negative infinity, and that's going to be positive infinity. And that's my answer. So it turns out in general that when the degree, let me write it out fully, when the degree of the numerator is greater than the degree of the denominator, and remember the degree is the highest power that I see. So the degree on the numerator is a 2. The degree on the denominator is a 1. So when that happens, when the degree of the top is greater than the degree of the bottom, the limit is either going to be positive or negative infinity. In this case, it ended up being positive infinity, and I needed to do the simplification to tell what it was going to be. All right, let's look at part B. So this is the next limit that we had seen before. All right, let's use this shortcut again. Highest power on the top is this negative 4x squared. On the bottom, it's the 16x squared. So keeping just those, we get the limit as x goes to infinity, negative 4x squared on the top over 16x squared on the bottom. This simplifies, so we get the limit as, in fact, wait, I don't even need to write limit, I think we can just cancel. 4x squared, the x squared and the x squared cancel, and I get negative 4 over 16, which simplifies to negative 1/4, and that's our answer. So the general rule here is that when the degree of the numerator equals the degree of the denominator, then the limit involves the coefficients of that biggest power on top, which is negative 4, and the coefficient of the biggest power on the bottom, which is 16. I'm going to say the limit is the ratio of, those are called the leading coefficients, the coefficients of the biggest power terms. All right, let's do one more part. So part C, this example also we saw in the last video, but I want to do this using the shortcut now. And I want to give you a minute to try this on your own first. So pause the video in 4, 3, 2, 1, pause it and try this for a minute on your own. Alrighty, so hopefully you've done that. Hopefully you paused it and tried it for about a minute on your own. So the biggest power of x on top is this negative 4x squared. On the bottom is this 2x to the 5. So keeping just those, we get the limit as x goes to infinity of negative 4x squared on the top over 2x to the 5 on the bottom. Now we can simplify this as the limit as x goes to infinity. We'll get a negative 2 left over on the top and x to the third on the bottom. So if we plug in, we get negative 2 over. We'll get infinity cubed. And infinity cubed is going to be infinity. And when you divide negative 2 by a huge number, that is going to get really close to 0. So that's what this is going to be. And the general rule here is when the degree of the numerator is less than the degree of the denominator, then the limit is going to be 0. So these rules that I'm writing down underneath each of these examples, these are for infinite limits. X has to be going to infinity or to negative infinity. And I want you to know how to do these infinite limits using this shortcut technique as well as the original way that we had learned it without the shortcut, which is not all that much longer, but I think it really helps illustrate this idea of why these highest power terms are kind of dominating. Okay, so let's do one more example. Okay, so we want to evaluate this limit as x goes to infinity. So we have some higher powers this time and simplify our answer. So if we use that same idea where we keep the highest powers, because there are a bunch of things being multiplied and raised to powers like this, I'm going to keep the highest power that shows up within each parentheses. So in the first parentheses, that's this minus 12x. And the next one, it's 3x, plus 3x. And in the denominator is that 6x. All right, so if we just keep those, we get the limit as x goes to infinity. Let's put an equal sign here. Of negative 12x to the 9 times, this was a positive 3x to the 6 over positive 6x to the 15. So now let's use some exponent properties. This is the limit as x goes to infinity. So when I have a negative number being raised to the 9th power, I'm going to get a negative 1 to the 9, which is going to be negative 1. So let me just stick a negative in front of this whole thing. And then I'm going to get 12 to the 9 times x to the 9. And if I use that same exponent property on 3x to the 6, we get 3 to the 6 times x to the 6. On the denominator, we are going to get 6 to the 15 x to the 15. Okay, so the easiest thing to see, I think, is that the x's kind of will perfectly cancel. X to the 9 times x to the 6 becomes x to the 15. That perfectly cancels this x to the 15 on the bottom. For the remaining terms, it's helpful to use some exponent properties. Okay, so for example, with 12 to the 9, I notice that 12 is 2 times 2 times 3, or it's 2 squared times 3. So I have that whole thing being raised to the 9. Similarly, for 6 to the 15, I can think of this as 2 times 3 to the 15. And now let's do some exponent properties. So this will be equal to negative. Okay, there are no more x's, so now I don't need to write that limit anymore. There's nothing to plug into. So for 2 squared times 3 to the 9, I can distribute that 9 to both of these terms because they're being multiplied. That'll give me 2 squared to the 9, and then times 3 to the 9. And on the bottom, I'll get, oh, whoops, and I still have the 3 to the 6. 3 to the 6 on the top as well. On the bottom, I'll get 2 to the 15 times 3 to the 15. Okay, 3 to the 9 times 3 to the 6, that is 3 to the 15. So that cancels with that perfectly. And then for 2 squared to the 9, I have a power to a power, so I multiply them. I'll get negative 2 to the 18 over 2 to the 15. That simplifies to negative 2 cubed, which is negative 8. And that's my answer. In terms of our goals, we've now talked about evaluating infinite limits of rational like functions using this shortcut.